Hello, everyone. My name is Nathan, otherwise known as Old Man Bills, and we have Sean Calderon here today. We also have the Benny Factor, and Gerald will be joining us in just a few minutes. And we have Sean that's going to present this morning, or excuse me, this afternoon. So, guys, you want to say hi real quick?
Hey, guys. Great to see
everybody.
you.
Okay. All right, Sean, are you ready to go?
I am.
All right.
All right.
Let me go ahead and pull up your presentation, and I'll pull both of us out.
Sounds good. See if I remember the steps you taught me. How are we looking, Nathan? Can you see my screen, Nathan? Hello? Hey, guys, did I lose you? Nathan?
Yeah, I'm here. It doesn't talk when I'm in the background, so.
Oh, did you see was it the correct screen?
It was, and you switched it back.
Okay, I'll set it up. Sorry about that. All right. Hey, everyone. Sorry for the technical difficulties. Nathan had walked me through some steps to how to improve the sharing of my slides. And of course, I fumble it and needed Nathan's help. So thank you for your patience. So I love taking photographs or videos of my experiments. And once I go through them, I find things that I think are interesting that I want to share with you guys. And so I hope you guys find this interesting. And so here on the first slide, we have the capacitor and the inductor. When I think about it, everything in the universe has a resonant frequency. And the way we can, I guess, capture or express or manifest a resonant frequency, we use geometry, geometric shapes, combinations of metal and insulators. And so that sort of describes here what we're doing. This is what is called the tank circuit. And we're going to go over this a little bit more. But to have the coil and to have the capacitor really gives us the tools to dig into the objects that have their own resonant frequency. If you recall from my first presentation, I had epoxied one of my coils after winding 5,000 turns of wire. And so one thing I haven't done yet is share me testing this coil. And so I thought I would start with this testing, and I'm going to be using the faithful ZVS. But you can see here, it's both has an artistic quality as well as a scientific one. Before we get started, I like to take screenshots of how my plasma is acting from my coils. This one fascinated with me because if you look over to the left, you'll see that there's a copper pipe, and you can't really tell, is it pushing electricity into the coil or is it pulling it? Nathan says it's like a pump, so I agree with that assessment. But I scribbled some stuff on this photo and wanted to kind of bring it up to you guys in the chat to see if we can come to some understanding. So on the left, you see here that it's connected to Earth. And so when you have this discharge, it looks like half of it's going to Earth, which is the path of least resistance, but then the other half is just going to nowhere. So is it really true that electricity follows the path of least resistance? In this case, it's not. I listened to one electrical engineer, and he used the analogy of is when you turn on electricity, it's like taking a bucket of water and then just throwing it into the air. And the water doesn't know what it's going to be headed toward. It just flies everywhere. And now if it hits an object, then the water is going to act differently. And for some reason, though, we can't imagine electricity that way. We always think that electricity is sort of waiting for us, and then we add our device, then it just flows through our device in this streamlined, perfect way, following the paths of least resistance, when really with this diagram and working with plasma here, it doesn't look like it's the case always. So before I get into the tank circuit, I wanted to go over sort of my take on electricity. When I start building a project, I have these sort of fundamental ways of thinking that help lead me to building working circuits. And one of them is just, here is the flow of electricity. I have a lot of squiggles like this from my iPad. So I hope you enjoy them. They're fun with colors, if not anything. And so what is the speed of electrons traveling in a wire? Well, they travel at 30 inches per hour. So when I first studied this, I was pretty flabbergasted how slow electrons move in electricity. And 30 inches per hour is pretty slow. Now, what they'll say is that if you take, or imagine a tube with some ping pong balls, and then you take a ping pong ball and hammer it into one end, and then another ping pong ball comes out the right here. They say that this causes an excitation of the electrons, and that excitation then causes an electric charge that travels near the speed of light and a magnetism that travels near the speed of light. And so I drew here in the bottom left corner, this is an electron, and it's electric field. An electric field, the lines just go straight out. And so when Mr. Lanius builds his electrets, the fields from the electrics will look just like this electron here in the lower left-hand corner. And I can't wait to see that. It's going to be like a permanent magnet, but it's going to have a permanent charge. Now to the right, it's still an electron, but now it's acting like a magnet. In fact, it does have a north and south pole, and it has these magnetic lines of force or flux bending around the electron. And so you have electric charge, you have magnetism here on the bottom, and then I combine it to you have electromagnetism. I'll dig a little bit more into this in a minute. So if you remember my electrons going through the pipe, flowing through the ping pong balls through the pipe, I took and wrote out or scribbled out some electrons along this line here. They're like these green circles. They look like peas. And so let's say this electricity is moving, the electrons, I'm sorry, is moving 30 inches an hour. But during that, they get excited and they create a magnetic field, which is this red part. And then it creates an electric field, which is this blue part. Now, these are the things that move across the wire, if you will, the conductor. These things move near the speed of light. So you don't have to wait for this lumbering, slow electron to kind of get with it and get to your lamp, which is, across the room. No, when you flip the switch, you're just exciting the electrons as they're moving slow, and you're getting these fields. And these fields are the ones that give us the electricity we need. We call it electricity to power up our devices. And so I was looking up electromagnetism, and I thought, what's electromagnetism? And I thought it was light, just light. But here I discovered it's light, it's electricity, and it's magnetism. So I thought that's interesting, because the charge and the magnetism that moves across the electrons, that gives us electricity, and that's electromagnetism. Yet that same phenomenon also gives us light, or is light. And then again, that same phenomenon gives us magnetism. So I thought that was really fascinating. Here we go with my drawings. So I want to dig a little bit into what a capacitor is. If you look at the top middle here, plate 1, plate 2, this all black, it has some circles in the middle. This is a diagram of a capacitor, and I've drawn it out where you have the two plates, and then you have in the middle an insulator. Now, when you take a 9-volt battery, so you can look at the drawing, the colorful one here in the bottom middle, hook up a 9-volt battery, and what happens is on the plus side, you're attracting all the electrons or the negative particles in the insulator on the right side here in green. But then on the negative side, on the green here, okay, it's going to attract all the protons on this side. And what you'll also know in the insulator is that instead of circles, the atoms are just circular, they get squished. These atoms get squished, and the positive gets squished to one end, and the negative gets squished to the other end. Now, these distorted atoms, if you will, they're like, think of them as like rubber bands. Once I take the 9-volt battery off of this, these deformed orbitals, these stretched out atoms, they're going to stay that way. And then if you take just a plain wire and connect it between the plates, then these stretched out atoms will, like a rubber band, snap and cause current to go into the other direction. And so you might have felt it where you charged a capacitor and you forgot and you grab it and it gives you a zap. That's because these deformed atoms are still stuck in this deformed state where they're pulling on one side and pushing on the other. Now, I wanted to mention a couple more things here on the capacitor. A capacitor resists changes in voltage. And the resistance a capacitor have is in ohms, just like a resistor. And voltage lags current in a capacitive circuit. And so I drew this sort of colorful sine wave here where it says volts in purple. And so as amps is moving ahead, it's in the blue, purple's trying to catch up, because purple, our volts are lagging because a capacitor causes a lag in voltage. When you look at the bottom colorful capacitor again, and in the middle between the plates are insulator atoms. These stretching of these atoms have a limit. And if the limit is too much, there's too much voltage on each side, and the atoms in the middle of the insulator get too deformed, they're actually just going to break and let loose current going through it. And so the strength that keeps these atoms from bursting and the capacitor becoming a straight shot, a short, is its dielectric. The dielectric is the strength of the insulator to not conduct. And so when someone's talking about the dielectric strength or the dielectric, oh boy, my brain's not working, constant, that means that's how strong it is, the insulator is, that you can put a lot of voltage on one side and a lot of voltage on the other side, and it won't conduct electricity. And so dielectric strength is important. Also, dielectric is constant. That's the word I'm looking for. A dielectric constant is also important because it'll have other properties that might be better than others. Even though you'll have two insulators that are good insulators, they can have a poor dielectric. And so you want to look more for the dielectric constant than you want to look at its insulative value as it relates to picking up good capacitors. And a real good capacitor that has a good dielectric strength I like is mica capacitors. But they're expensive, so I'm trying to build my own mica capacitors, and I'll present that in a future presentation. Now, a capacitor stores charge. It stores the electric charge as its energy as an electric charge, and that's going to be important here in a little bit. Oh, this is even funnier. This is on the left here is a coil that's not connected to anything. And on the right here, with these red gaudy lines, when you apply power, we'll apply 9 volts, then the coil here becomes a magnet, It has a north pole and a south pole, and it does everything a permanent magnet does, except for it's only a magnet as long as you have the voltage. Once you don't have the voltage, then there's no magnet. Now, with a coil, which are called inductors, current lags voltage. So if you don't have a capacitor, but you do have a coil, then you're going to find out that your amps are lagging your voltage. And so a capacitor pushes back on voltage, and a coil pushes back on current. And that pushback, that resistance is measured in ohms. And like the capacitor that stores charge, a coil stores magnet energy. So one is electric energy, and this is magnet energy. And so now just digging a little bit deeper into these two components, now all my presentations should look like this, right? This is a tank circuit. Here you have the coil on the right, and it has those magnetic lines of flux that I shared with you earlier. So it's acting like a magnet. And then here we have the capacitor. We have two plates. One you can see on this side. There's one on the other side. And then the red material here, that's the insulator. That's where the orbits of the atoms are being distorted and holding a charge on those plates. And so when the capacitor discharges, then it powers up the coil. Then when the coil discharges, it powers up the capacitor. And this back and forth is called oscillation, or it's called frequency, or cycles. That's another word for it. But this here, this tank circuit, this L, which is the symbol for coil, L, and this C for this capacitor, this is an LC tank circuit. And that's all it is. That's why when you use the ZVS, which we'll talk about here in a little bit, you only need to be focused on the capacitor and on the inductor, because what you're trying to form is a tank circuit at a particular frequency. I think I already said everything that's necessary in the first diagram, but this is my attempt to explain it. And so you have this tank circuit in the green, it's going one way, then the other way, and so back and forth, oscillating, and frequency, they're all the same thing in a tank circuit. Okay, so this one is, I hope it's explanatory. But I want to explain and spend a little time on this, because this sort of explains Nathan's experiment. That is, I think it's a next level experiment that Nathan just performed recently, and here I hope to tell you why. Now, a ZVS circuit can only be thought of as just two MOSFETs, and MOSFETs are switches. So when one MOSFET's on, the other MOSFET's off. So over here on the left, you'll see ZVS. You'll have these two MOSFETs that are marked by 260. And that's all they're doing. They're just oscillating, creating a frequency. Now, what frequency are these MOSFETs switching at? Well, it's determined by the capacitor and the inductor. Those two values determine the switching of the ZVS. And these are going to switch oscillate at the resonant frequency. Now, if you look in the lower left-hand corner for you math buffs, if you take 1 over 2 pi to the square root of L, which is the coil, and C is the capacitor, then that will give you the resonant frequency. So if you know the capacitor's value, you know the coil's value, then you run this little formula here, and then you know what the frequency is. Now, once this circuit here on the ZVS starts tanking, oscillating with a frequency, that then affects the Tesla coil, the actual coil that you see where the sparks come out of. Now, it's worth noting that this part of the Tesla coil, the secondary, it is not connected to the ZVS at all. There's no wires or anything that connect the ZVS to this coil. The only way this coil receives energy is in the coil on the left here. As it's oscillating, it's going to push its magnetic lines of force over into this coil. It's going to spill over to the right here. And when that electromagnetic lines of force hit this coil, then it induces this coil to then begin to oscillate. So the primary coil, the primary capacitor, and the ZVS, they oscillate because they have a capacitor and a coil. Well, now we have a coil, and wait a minute, we need a capacitor because it's also a tank circuit. Oh, here we go. The coil here, the Tesla coil, has a capacitor, and it's the air. And it's the air that connects to ground, and then the air that connects to the top of the Tesla coil. And so what happens is that this coil, coil 2, outputs here out the top. It hits the air forms into a capacitor. The capacitor then uses the ground, and then the ground comes back up through the Tesla coil, and how you have this now tank circuit. So now you understand basically how a Tesla coil works, but here's something Nathan did. He takes a wire from the Rodin coil here, and he takes it over and puts it into the top of the Tesla coil. Now, what he's doing is he is now tuning this Rodin coil to its own resonant frequency. And what this Rodin coil does is it begins oscillating with, again, another air capacitor. It's just using the atmosphere around it. And what's so cool about this tank circuit, because it's just the Rodin coil disconnected. I mean, what's in the Rodin coil? Well, the Rodin coil has magnetic energy. And then because it's connected to the air, it's going to form a tank circuit. And so when Nathan put that fluorescent bulb on top of the Rodin coil, what he was doing in effect was extracting the power of the Rodin coil, oscillating with the air around it. And the fact that the light stayed on for a couple seconds really tells you how well tuned Nathan was able to get the Rodin coil to probably its perfect resonant frequency. And I haven't really seen that good of a transfer at resonant frequency that Nathan has done with these coils. But this is what excited me, because if we can have a way to have a wire out to push something that is so efficient and can oscillate it on its own, we may be able to have an opportunity to put equal energy in, equal energy out, or even better. Now, I know that's blasphemy to the current scientific world, but I see a lot of promise in this, and I'm going to be working on an experiment to build on what Nathan's doing here, because I really think he's done something big here. Now, I'm not going to compare the ZVS on how it works internally or how a Slayer exciter works internally. I'll do that in another presentation. But just to know, the Slayer exciter has one MOSFET that switches. The ZVS has two MOSFETs. And pretty much all Tesla coils are designed this way. Instead of it having a solid state buildup like this, they can have a spark gap, and the spark gap becomes their switch instead of the MOSFETs. So there are different kinds of Tesla coils, but this is just an overarching view of how they're configured. So I started playing with taking snapshots of the output from my coils, and I thought they were fascinating because there's a lot of intricacy in the plasma discharge. One thing I was doing is I was taking the more interesting discharges, and I was looking at them under different filters. And this filter was allowing me to kind of see more what are the more solid parts of the plasma and what are the less solid parts. And it's just fascinating to me that it looks like exactly like a tree in winter. And just the fact that um, this chaos is really this plasma is really a mirror of the nature all around us, the trees and the plants. And so I just wanted to take a couple cool ones and share them with you. So this is a snapshot before the filter, and this is after the filter. So this is a different filter. Again, if I were to show this to somebody, they'd be like, "Oh, you got a black and white photo of a plant." No, no, that's plasma. Pretty interesting. And this will be the last one. This one is pretty interesting. And again, the solid parts are fascinating as compared to the least solid parts. So I printed a new sphere and a new stand. Big credit to Brian Brum. He's my buddy. He is a master at 3D printing. So I work closely with him to come out with these cool designs. And I just thought before I wind this, that is just too pretty not to take pictures of. And also, I just ordered some copper tubing. So I'm going to swing some copper tubing around the stand here so it looks like vines. And then I'm going to position the copper tubing to be more like art, but yet it's also going to be functioning. And my goal is to build the power supply to have this output 1,000,000 volts, quiet and on your desk or in the corner. And so it's more going to be functional art, which I'm pretty excited about. So of course I have a lot of different pictures of it. Very cool stuff. Actually, I wanted to show you one thing here that I changed. If you look up here on the upper right corner here, where my cursor is, you can see that how deep these grooves are. Usually they're only about a 1/2 centimeter deep. This is a full centimeter deep. So this allows me more flexibility and how much wire I want, what gauge wire I want. And so this extra space is going to be really helpful. So I'll be sharing more about this when it's built. All right. All right. So Nathan asked for the 3-step method I use to build a ZVS circuit that will provide a large plasma discharges in whatever coil you put it in. And so the first piece of equipment you're going to need is the LCR meter. This one's the best for its price. They can get very expensive. I think this is on Amazon. I bought it over a year ago, so I don't remember the price. But I use this every day. I use this so much. I mean, it's like a must-have. Once you start measuring all your coils and their inductances and their Q, you get to find out their quality factor and their efficiencies. You're going to get hooked, and you're going to go, "Oh my goodness, I'm going to wind this again because it had a high Q," and that Q means it's having a higher or lower loss of power. Here I'm using the LCR meter on the 1/4-inch pipe, which is the primary of the Tesla coil. And I have here 6.4 microhenries. You can see that here on the LCR meter. On top of that, it has 3.08, which is the Q. It's not a very high Q. But you'll notice in the upper left-hand corner that it says 1 kilohertz. Let me see if I can make that a little easier to read. Here we go. It says 1 kilohertz. You can change the frequency when you're measuring your coils, and that'll give you insight. For example, if I go to 10 kilohertz and the Q drops, well, that's not a very efficient coil. But let's say you put it up to 100 kilohertz and the Q is off the charts high, and you know that your Tesla coil is going to oscillate at 100 kilohertz, then you know that coil is going to be perfect. So some info from the LCR meter. And so I'm going to take this value right here from the LCR. And I'm going to get my second value. Yes, you see, I like gaudy colors. It's sad when you laugh at your own stuff. So this is a 3-step process for figuring out the resonant frequency of your secondary coil of the Tesla coil. So this is a oscope here, a signal generator, a 6.k ohm resistor, 5 to 10 k ohms can work. And yeah, you need these two things, and you'll be able to discover what your resonant frequency is of this secondary coil. I show over here on the left, good is a very small signal and bad is a very high signal. This is kind of an oversimplification, but what you're looking for is the lowest amplitude frequency. And once you hit the lowest amplitude frequency, then you know the resonant frequency of coil 2. So now in coil 1, we know the inductance. Here in coil 2, we know the resonant frequency. So there, clicked too many times, sorry. So here you can see that we have the input of inductance of the primary. We have the resonant frequency. These two inputs will then calculate our capacitor. And that's why I do this. I don't use the math or the formulas. I know some of you guys can, they're good at it. Instead, I just Google resonant frequency calculator. I put in the primary inductance in henries. I put in the resonant frequency of coil 2, and then it spits out my capacitor number. And this is really great because you don't have to put the alligator clip. So let's say I only put in the capacitor value and the resonant frequency. I'm sorry. Let's say I have the capacitance, but I need to find the inductance with the alligator clip. And so Nathan has shared that with you, and I could share it with you as well. Moving that alligator clip on that copper pipe every millimeter, and it changes. This method just says, you know what? Measure the copper pipe that's going to go around your coil, and then measure the resonant frequency of your coil 2, and then it'll spit out your capacitor. Now you might say, well, I don't have a 500 nanofarad capacitor. We'll cover that in a little bit because you don't have to have every kind of capacitor, and I'll show you that in a little bit. Now, this is my setup for the plasma displays that we're going to observe. Over here, you see this piece of copper, kind of looks like a little cobra. That's connected to ground, if you see the little alligator clip there. And then you'll see the bowl-shaped copper pipe, and that's the primary coil. And so this bowl-shaped copper pipe, this little capacitor over here, they're going to form a tank circuit, and they're going to oscillate. That oscillation is going to get into this coil 2, the secondary coil, and then this tip out here, electrons are going to come to the tip here, and then when they come out, they're going to use air as a capacitor, and then it's going to go back to the ground. And so this coil is connected to ground. It outputs out into the air, uses air as a capacitor, and then connects back to the ground. And that's the oscillating tank circuit for this coil here. So pretty fascinating. Now, I'm looking through my notes here. So this is, I've made some mistakes, and I'll have to confess, I need to apologize. When I was making my voltage readings, I was using the meter that's on the Variac. Well, the meter on my Variac doesn't work, and I discovered it the hard way. And so instead of using my Variac, I'm using my Fluke meter, which is calibrated and it's a great meter. And so what I'm doing here is I'm doing tests determining voltage and amps that break an arc at different distances. So in this one, the arc breaks at 1 inch, and that's 10 volts input with 1.9 amps. Go to the next one here, and this is 2 inches, believe it or not. And at 2 inches, the ground here on the left and the plasma breaks. That's 14 volts and 2.6 amps. And now this is 3 inches. And so it has to really put out the voltage to find it. And at 3 inches, this is 19 volts and 4.5 amps. Now that's the input. Those are the input voltages, 10 volts, 14 volts, 19 volts. These output volts are 75,000 volts for the 1 inch, 150,000 volts for the 2 inch, and oh boy, can't do the math in my head. 3 times 75,000 volts is this one right here. And so to go from 19 volts, 4 amps to 3 times 75,000 volts is absolutely incredible. Absolutely incredible. And I'm going to show you the maximum here, and it's for this coil that we haven't really tested. And I hope you guys are surprised as I am.
Hey, Shawn,
Yes.
real quick, can you go back to the last video?
Yes, yes.
Can you pause it as soon as the plasma pulls from the ground?
Yes.
Right, oh, just a little bit before that.
Yep. Let me go back here.
Just let it play through again and catch it.
Okay. It's interesting that the color gets like that touches the ground wire, gets fluffy. It's almost like a plasmic flame. Here we go.
Okay. Just,
go back right there.
Okay. You see it starting to pull. It's just right there. Just pause it. Of course.
No, I can pull it. Let's see here. Here we go. Come on.
Right there. Hold on. You go a little bit further back, just a tiny bit.
Yeah.
Okay. You see it's pulling from the ground wire first. You see the plasma discharge already on the ground. You already see it on your Tesla coil.
Yeah.
And when you watch it in slow motion, you'll see that it pulls it directly to your Tesla coil and starts interacting with the voltage.
It's being pushed right. The earth is pushing it right out at it.
So you said earlier that it was going back into the earth, but it looks like, in the way the Tesla coil works, is it picks up extra voltage when you put in the ground wire to the earth. So it's showing right here that you're pulling energy from the earth to get to your Tesla coil.
100%, because the plasma on the right, the big plasma discharge on the right, that's connected straight to earth ground. So what I do is I connect that one to earth ground. Then on the left, I connect that to another route to earth ground.
So you're double grounding. So without even knowing it, you're creating a capacitor in the ground in order to pull the voltage out of the ground.
Exactly.
And your pump is your Tesla coil. So you'll see that the energy coming out of the ground wire will go and spark like a pump does, just like your Tesla coil does.
Right.
So you know what loop is in your circuit right now.
It's, you've shared some presentations on this, and you've envisioned this, and now I'm just starting to understand and realize it. And it's so cool to have these breakthroughs in my own mind. So I appreciate that, Nathan.
Sorry for stopping you on your presentation. I just wanted to point that out because it just tells you that there's something going on in the earth when you're putting both grounds in and double grounding a system.
Yeah,
That's very important here.
I agree. I agree. And I'm glad you're bursting in because I thought maybe someone's falling asleep. So I appreciate that.
Oh, no, we're all here watching.
Thank you.
You know what, hold on a minute. We'll say hi to Gerald real quick.
Okay.
What's up, Gerald?
I'm kidding, Shawn. I love your work, buddy. I love it. I'm telling you. I just had to do that just because you mentioned him.
Oh yeah,
It's awesome. I've learned a whole bunch from you. So
thank you so
we'll
much.
get into that in the future, though. I guess. Yeah.
Okay, Shawn, you can go ahead with your presentation.
I'll shut up now.
Okay. I'll just say thank you so much. I learned so much from you, Gerald, as well. So I really think we're a great team. I can listen to you tell stories all day, Gerald. So thank you. All right. So let me see if we'll finish this here and we'll kind of see. Yeah, I can't pause it in time. All right. Let's see. Some of these I don't remember, even though I did put them in the presentation. Let's see. Okay. Oh, I see. This is me running at 30 volts, and I have the ground over there on the left. It's actually 6 inches away now, and I just thought it was interesting because it almost feels like it's feeding them in like sort of invisible electrons and making this bigger. I thought that was just worth noting. And when it discharges or strikes, it's like a completely different color. It's like yellow. And I'm not sure why you get yellow when everything else is violet. So just something worth looking at. It's fascinating to me. This is another thing that fascinated me. So I like to just make coils and electrocute things. And here I had this trusty martini glass that was very helpful. And I put a coil in over around it. And then I put the earth ground, and it doesn't want to go to where the electricity is being discharged on the top. It wants to go through the epoxy, which is way more resistive than the air. This should just be a straight line or close to it. And so what I'm guessing is that this coil of copper pipe here is creating a magnetic field that's pushing the electrons down. I'm sorry, I have a whiny puppy here. Come on. Okay, good boy. So this fascinated me because it's just not supposed to do this. It's just not. It's not. I mean, it's got a perfectly good copper wire here, and it's choosing the top of about almost a ½ inch of bubble-free epoxy, which is a massive insulator. And so this was interesting to me. Just like to see it one more time. Way crazy. Let me talk about that later. So, oh yeah, so I took away the ring, and now it's touching it a little bit, but it likes now really connecting to the top discharge here on the right. So yeah, that ring has an effect because you saw it. All the plasma was going straight into the epoxy, whereas this, you can see it. It goes just touches the epoxy here and there, but it's nowhere near the other one. So I wanted to point that one out. And of course, I have to do my top view like I did the sphere. This is a very different coil. It's a cylinder, of course, but it also has more turns of wire. And so I thought I would share. This one has a lot more output energy, which was affecting my phone more than the sphere. So I had to maintain a little bit higher distance from it. But I just thought you guys like to see this new coil and the pictures from the top. It also has a deeper purple. Doesn't have the more violet, which is also interesting. I don't know what that has to do with the geometry of it, but It's definitely a different color from the top here. And I'm not using any filters, doing anything with the camera. All right. So I think this is my last one. This is 30 volts, 5 amps, and it has a real quiet sound to it. I wish I could adjust the sound for you guys to hear it. It has a quiet hush. And so I'll just put that on in the corner. It doesn't create ozone. I guess it's the wrong frequency. And it's just something peaceful, nothing fancy. All right, so I went to the thrift store and I found this gaudy lamp that had these bulbs, these glass spheres going up and down the center rod. And it almost looked like a little chandelier. And so I thought, well, you know what? I need these glass spheres because someday they'll come in handy. My wife was rolling her eyes when I told her that. I know husbands never get that, but I'm just that rare case where my wife rolls her eyes at me. So you can see the hole goes through, and it's solid, it's thick, it's heavy. It's a solid piece of glass. When I had run plasma through it, it started putting cracks here in it. And so I thought I'd share that. And the reason why I'm sharing the cracks first is because when you start seeing the cracks while you're watching the next displays, you're going to see what the electricity does to the cracks, which is subtle, but I hope you catch it. All right, so this is my first test. I put the glass sphere right on top. And again, the ground is on the left. And again, it's strange. It's going through the solid glass. The path of least resistance would be over the glass and down the chute. Glass has a higher insulation value than the air around us. I mean, air is not a conductor, but so this really interested me. This whole thing about earth ground and this push and pull on how it just pushes and pulls through it's about 1.5 inches of solid glass. I think I have some different shots here. There's another one. This one I just thought, let me just turn it on with no ground wire on the left and just see. And it's really interesting how it just funnels it. Pretty interesting. You can see my messy setup on my desk. Now here I move the ground higher, so maybe it'll want to go and connect to the top conductor, and it does. But if you look over here, there's the little leak right here. See my arrow? It's leaking plasma because there's a crack in the glass. How is a crack in the glass like a little wire? It's amazing to me. But you can see it there clearly again. I know this is nerdy stuff, but it's just fascinating on how it's reacting to this piece of glass. Last time I was clicking a little too fast. So yeah, and here's my setup. See my ZVS over there on the left and a bench full of junk. Let's see, this is a different one. Different angle. Yeah, this was a lower angle. So again, very fascinating. It's choosing the glass or the epoxy. Pretty cool. I can turn it up quite a bit inside the glass here, and it just draws more from the ground on the left. So it doesn't want to kind of jump out too much when the ground is at this level. So I'm just kind of moving the ground wire on the left here around and testing different things. And let's see this one. I think this is just another display without the ground. Yeah. Oh yeah, I'm hitting 30 volts with this one. 30 volts, 5 amps. And I'm trying to catch the length on the top. So yeah, it's about 10 inches, 12-inch arcs. The glass is definitely having an effect on its form and its color. So that's really cool. Yeah, just fun with a piece of glass you got at the thrift store. It's pretty interesting. Almost done, guys. Thanks for your patience. Let's see. There we go. So when I'm figuring out the primary coil that's going to go around the secondary coil, I wrap the copper piping around in different shapes, and I'm just trying to see how what's the right adjustment for the Tesla coil. And what you're seeing here is what you don't want, and that is the copper pipe is literally connecting to the wires under the epoxy. If you do this long enough, it'll actually throw chunks of your epoxy out, and it'll melt it, and it'll char the wires on the inside. And so this is a bad thing, even though it looks cool. And so part of my tuning is to weed out situations like that. Here's what it looks like in the dark. It's kind of cool. Looks like a gas burner or something. And so something to be concerned about. And so here I use the concave. And as you've seen earlier, the concave has worked really well. Now, this concave coil here, this bowl-shaped coil copper pipe, has this little tiny resistor here. All of the hundreds of thousands of volts, all the plasma discharges you saw was with this little tiny dinky capacitor. Everywhere you look, when you have a plasma discharges this big, you have a bank. People will have a bank of capacitors, and they'll have a big, neon sign transformer, and they'll have just all this heavy duty stuff. And oh, well, I'll have to, do 20 capacitor banks of 20. And I don't know. I don't know why the direction I'm taking is ending up with such little capacitance. When I add capacitors to come out at the same value, if I follow the conventional wisdom, I actually reduce the discharges. So when I want to increase all that plasma, all those hundreds of thousands of volts, I have to take this little tiny dinky capacitor and connect it to this soup bowl shaped copper pipe. Should be chilling water behind a refrigerator filter dispenser. And yet we get these beautiful discharges. And so I thought that was worth mentioning. If you recall earlier that if you're able to find the inductance of the copper pipe or the primary coil, if you're able to find the resonant frequency of coil 2, the one with all the thousands of turns of wire, then number 3, it will tell you what capacitor you can use. And so instead of buying every different type of value capacitor, I came up with a different point of view. I shared one in my first lecture, but I think this one's better. And so with the 20 capacitors, they're all at the same level. I would measure between the prongs, and I got 37 nanofarads, 26, 16, 110, 14. So you can get, I was writing up to 65 different values of capacitors. And so this will save money because instead of buying the exact capacitors every time, I can just alligator clip the ones I want for the prototype. Now, if you do a little algebra and as it relates to permutations, these 20 capacitors each have 2 leads, so 40 leads. There's a billion permutations that you can derive from this. I don't know why that's even mentioned. I think only Sears will understand it, Victor. But I thought that was worth mentioning. But I got 65 values that I like. And so if you want to just buy 20 capacitors that are cheap, all the same, hook them up where you can have some posts sticking out, and then use your meter to tell the capacitance and just write it down, and you'll end up with 20, 30 different capacitors or more. So I placed some resistors in a helical type shape, put it in a form, and then put it in the vacuum chamber. This is epoxy. And I did the math. So the resistors are 500 million ohms. And this can measure up to 30,000 kilovolts. And I wanted this to see what are the waveforms in every part of my Tesla coil circuits. So I thought I'd show you. I'm not yet all done with this process, but I thought I'd show you. I'm sticking this giant homemade probe and testing the gate here of the transistor. Now, the reason why I'm not sharing you the oscope readings is because I need to build a Faraday cage for my oscope. My ZBS board can be 5-6 feet away from my oscope, and it will still show the output frequency of the Tesla coil. So I have to figure something out. But I thought I'd share this. This is one of the things I'm working on. Pretty cool stuff. So I want to give credit. I Sharpied out his name here, which is not cool. It says here schematics. He has a YouTube channel. He offers his induction heating board designs for free. I just took his and repurposed it and altered it to be a high voltage ZBS circuit. But I just want to give credit to him. As you can see, each square here should have a capacitor rectangle, but that doesn't work for our purposes. But I want to give a shout out to Schematics. He has a very interesting channel, great guy. I recommend subscribing. So here I took the top view. I just wanted you to see how small the capacitor is as it relates to the other circuitry, and how this copper piping here and this little capacitor can cause so much plasma. It's really fascinating and amazing to me. There's a little capacitor that could. There's my pinky. I'll show you how small it is. And it's 0.33 microfarads. Let's see here. 0.33 microfarads, which is 330 nanofarads. And here it says 50 kilohertz. So it can handle 50 kilohertz. But I run them at 100, 200 kilohertz and they do fine. These, they're cheap Chinese, but the Chinese got it right here. These are really quality on their other circuit boards. This is, I recommend, it's winter time, so I don't have good ventilation, can't keep the windows open. And so I bought this little ozone meter. And when it gets into moderate, I have to think of something, maybe put the fans on and take a break, because that's when my throat starts to get sore. Good to slight. I mean, it's killing the germs. It's probably good, but I get uncomfortable at moderate. So this beeps, and yeah, it's a cool little meter, and it's not expensive. I'm working on the hot rod. I want to have this for next presentation, and I'm going to hook it up to that coil, the coil that we've been working on through this whole presentation. So I'm hoping for some big things. So I have a cottage out in the woods. This is 5 acres of the 85 acres I own. This is a lake. My wife and I, we bought this lake, and then we bought the forest up there in the north. But I thought I'd end up with this. It's just peaceful. It's fall. And this road here that we came in on, we get a high traffic day, we'll get a single car. 2 cars is rush hour. So yeah, just quiet, serenity. And I thought I'd close with that. All right, stop sharing.
Man, serenity now. Let's all go there.
I'm moving in, Shawn. I'm just kidding. I'm kidding. That's beautiful. Good for you, man.
Yeah.
Yeah, that's awesome.
Appreciate it. Thanks for listening, guys. I know it's a long one.
Yeah, well, since you're on the lake, we might go fishing a little bit too.
That's what I'm talking. Hey, my wife and I are building bunk rooms on the bottom, so you want to come up, stay a weekend? Let me know. I mean, it's a drive.
Oh man,
Nice.
that'd be fun. Yeah, you're in Chicago though, right?
Yeah, that's where our primary house is. The cottage is North Wisconsin Woods,
Oh.
central North Wisconsin, where you can get land for $500 an acre.
Oh, nice.
Yeah. I mean, it's wild. I mean, bears, turkeys, eagles, cougars, giant snapping turtles. I mean, the list is endless. Yeah, it's the wild.
I grew up with all that except for the turtle part.
Not-
When you decide to buy your own island, Sean, we're all coming to you.
Yeah.
You have no choice.
Yeah.
We're all getting out of this rat race.
You're all invited. Yeah, done. Hey, if society collapsed, I'll send you my address. So
hey, don't worry. I'll throw on my overalls. I'll come down and chop down some trees to make this cabin.
Nice.
I have a special trailer I don't talk about that I could bring.
Nice.
You hit a button and 8 solar panels raise up, and it's 5,000 watts. So
it disappears at night, and then it starts smoking during the day. So don't worry about that smoke, though.
So, oh my goodness.
Yeah.
Oh.
Yeah. So
that was an awesome presentation, Sean.
Thanks.
Yeah, that was cool.
Yeah, I think we better give him a hand.
Yep.
You guys are too nice. Thank you so much.
Awesome work.
Thank you. You guys have any questions? I know Nathan had one.
Oh,
about the charge pump.
No, go ahead. We're good. I already asked the question in the middle of the stream. Are you talking about somebody else on the stream?
No. What was I going to say? I wanted to ask you something, actually.
Oh,
what did you think about the Rodin coil and using the air capacitor as an oscillator?
Well, it's possible. What I would say is it just needs a lot more testing to find out definitively what I'm doing. Yeah. But being the fact the way the Tesla coil is working, and it's hot on the outside, cold on the inside, and I'm pulling it directly in, as long as I don't overcharge the wire by leaving a sharp end on it or anything like that, where it could pick up energy like that, I think it'd be better off. But let's just say the rate of dissipation changes in the room sometimes. So it's hard to account for everything in there, but it could be the air, and it could be changing the air around it.
Was a Rodin coil grounded in your setups?
No.
Yeah, that's why I didn't ground it. It's just oscillating with the air.
It's one wire system. Goes straight from that wire straight in there.
So I drew it right because, I mean, and that's what gets me so excited, because there's no way you would have it lingering that long if it wasn't perfectly tuned to its natural frequency.
Oh, I thought it was hilarious. I just pulled out the wire and put it right in front of the camera, wiggling it. You know what I mean? Like, buddy, it ain't connected to nothing.
If you charge a capacitor and with a coil, you can control the time of how the capacitor will discharge. So capacitor can discharge 2, 3, 5 seconds, however you design it. With the air as the capacitor and it's discharging that slow, it's really, that Rodin coil is really altering the air around it, or the atmosphere around it. I don't know what to say. It's just that's the best theory I could come up with.
Let's just say this way, it is changing the temperature in the coil because it's coming in cold, so the heat doesn't dissipate right away because there's not a lot of heat into it. So the heat has to come from the outside air back into it. So just remember that it's cold on the inside, okay? And then the heat from the air on the outside has to come back into it. So the more that it's lit up, the more it's pushing it away. We're playing with a lot more than what we should be probably playing with at this point in time, but it's cool.
Oh yeah.
There's so many things that you can do with that, with your discovery. I mean, to string along, I mean, you could run with a line, a wire that's so thin, like you can't even see it, thinner than hair. And you can string it along these rodent coils or the other coils that have longer energy. And you're basically transmitting tons of energy over, because it's running on the outside of the wire. It's charged. It's electromagnetism.
So here's the thing. Well, a lot of people think it goes inside the wire. So thank you for pointing out that it goes on the outside.
And it accumulates.
So the next process is I have to put the rod down the coil, okay, but into water. And then it has to travel at least 10 feet and go to the second Tesla coil with the rod down in it and start it up. So we're going to just play with a little bit of water. We're going to create some, water voltage here on the next one. And then we go to the earth. And you got to take it in stages so that nobody could say anything that you screwed something up or anything like that. So we're just take it slow. Yeah. But it's important to know why I keep pointing out to you that your coil is pulling in the energy from the ground.
Right.
So that you could start to see the actual loop that you're creating. Yeah. And when you create something in that loop, your energy, by the way, was different coming from the ground than it was coming out of your Tesla coil.
Yes.
Yeah. Go ahead, Gerald.
When he said it was fluffier, there's a part that none of us take into consideration. You're not, you can't see it. It's the energy that goes before the plasma that shoots out that you can't see. Think of lightning. So when lightning comes down from the sky, or so we think, it's actually reaching up and hitting a point, and then the lightning shows up that we see with our eyes.
Yeah.
So from what I saw in your coil, it was coming out of the ground, but there was an ion channel that happened before that even came out that you can't see. And that's why it's fluffier. It builds upon it.
Interesting. That is so cool.
So does Shawn ground the secondary of his Tesla coil? I could say yes, he does.
Only with the ZVS, though. I don't ground Slayer Exciter.
Interesting. I didn't either. There was a specific reason why not to.
Yeah. Good question, though.
Does Ben have his own channel? Yes, he does.
Beneficence TV.
Ben, if you drop that in the description or in the chat, I should say.
Yeah.
Ben is the man.
Chat.
What's up, Lulu?
Hey,
oh,
Lulu.
cool.
Hello, Lulu.
Oh, man, Ian's got a couple of them. Ian's got a couple of rodent coils that I'd like to put some Tesla coil energy into. It might just produce an awesome result.
Ian's building the Death Star. He's like close to being done.
Oh, nice.
It's gonna be cool. He's more anal retentive than me. He has like the cool little counter every time he winds it. I'm like, I just wind it till it looks right.
Oh, come on, Shawn. No, I built some stuff with Shawn. He's a drill sergeant behind the scenes. Let me tell you that right now. He acts all nice on here.
Yeah.
Old man Bills gets that line. Yeah, just like that. Focus, Nathan. Focus. We're doing this in this way.
Yeah. Do what God say, maggot. Love that stuff. Never mind.
Oh.
It's like a good dose of wake you up in the morning. You know what I mean?
Yeah.
Oh, it's so good, man. Oh.
So questions in. So what were your thoughts?
Yeah,
Gerald?
so when you said it didn't follow the path of least resistance, that was just my point when I was bringing up earlier that there was like an ion channel that goes before your plasma line comes out. that we don't see. So there's always a path of least resistance. But in the Tesla coil, you don't see it. In my coil, it was designed for it to follow the path of least resistance. And it's when you hit a sphere, most people think, okay, so your energy is going to go around the outside of the sphere, right? Because of your skin effect.
Yeah.
But scalar doesn't work that way. Think of it kind of like this. If you were walking, let's say you were going to school and you had to go around this corner yard, right? And it's just a grass yard. There's no fence or no nothing. Are you going to walk to the corner and then go up the street? Or are you going to cut across that yard?
I mean,
So,
unless just porcupines or something.
Yeah, well, exactly. So that path that you go, that least resistance, that's kind of how I designed the coil to follow that path. But with a Tesla coil, you're giving it that path.
Yeah.
But you don't see it because your eye can't pick it up.
That makes sense.
That's the only difference. But you have it. Scalar's there.
Interesting. Yeah, I'm still learning about scalar waves.
Yeah, it's interesting. It's the Zitterbuergang. You guys know what that is?
No.
So, can I tell a story? I don't mean to interrupt, but it kind of goes to what we're all working on here.
Okay.
Yeah, go ahead.
So Richard Feynman, famous physicist, came up with a word called the Zitterbuergang. And people use it. In fact, there was a video that came out recently where one of the scientific community was talking about it.
Oh, no.
Yeah, and what it is, I've got the description. I'll just read it out. It says the Zitterbuergang is a local circulatory motion of the electron presumed to be the basis of the electron's spin and the magnetic moment.
Oh my goodness.
So it goes on to talk about the Dirac equation, Dirac's theory and stuff. Here's the funny part. I heard a little story. Don't know how true it is. Maybe Jack could confirm, because I heard that Jack knows about this story. So Richard Feynman was sitting around with his cohorts, and they're all talking about physics. And if anyone who knows Richard Feynman knew, he was kind of an egotistical guy. He liked women. Everybody knew that. It's no secret. It's not a conspiracy. All the power to him. I ain't faulting the guy. So, as arrogant as he was, they're all sitting around talking and laughing. And he says, "Oh, my students, they're just so dumb. It's incredible." And the guys were laughing, going, "Come on, you got to give them more credit than that." He's like, "I'll show you how much credit I'll give them, okay? I'm going to come up with a word, and I'm going to put it in a paper. And then somebody comes in and interrupts him, was talking about how the ether is never let go." And he was ranting. I can't remember what scientist this was from the story I heard. And he says, the ether. Everybody's got a word. He says, "I'll tell you what. Zitterbuergang. So I'm going to call it Zitterbuergang. I'm going to put it in a paper." And he says, "I guarantee you, my students will eat it up and nobody will question it because we are the ones that make physics." And they all laughed.
Yeah.
So I don't know how true that is.
Oh, it's true.
Give me a break. Zitterbuergang. Man, you might as well call it, I don't even know, maple syrup. Like, seriously, you know? Come on. It's spin and magnetic moment that we all know.
My daughter's a physicist for Northwestern. It's a bigger physics program than Harvard. And she got a full scholarship. And she would tell me, "Dad, all the math, you have to put in so many like fake parameters, fake numbers." She said, but by the time they get to a conclusion, she's like, "How can you even trust it?" And she was telling me, and I'm like, I don't know. So yeah, it's kind of supports what you're saying.
Yeah.
Okay, I got one for you guys. Victor's telling us all the secrets here. Scalarism wave is a magnitude like temperature or barometric pressure.
True. Very true.
Oh,
yeah, I use scalar wave just to kind of describe like the ether in wave form. So if I'm wrong, thank you for correcting me.
Yeah, thank you. I was wrong too.
Yeah.
3D
I think
havoc.
that's what Ken Wheeler also describes it as. Not a wave, but like more like a field.
Yeah.
Huh.
Well, it acts as a wave because you're moving the field. You move it in such a way that it's actually part of my theory where you're
So,
shaking electrons. Go ahead.
so when I show you my Tesla coils experiment and I'm telling you about temperature, please understand what I'm working with here now. Not you might start to kind of figure it out. That's why I say there's a lot more here, Sean, than what you think there is.
Yeah.
Sean's got it. Sean's got it. You may not, Sean, you may not understand what you've got, but you got it.
Thanks.
I know Victor's got it.
Yeah. Victor is the mathematician that we need at the forefront of this.
I gave a
Yeah,
an
Victor's
equation
on the
for
next
him.
level.
Sorry, go ahead, Sean.
Oh no, I did give an equation for him in the presentation, so that was just for Victor.
Okay, hold on. So Ian says here, Victor, do you think forming a scalar static field creates a faster than light medium to transfer information? By the way, it's not static, but it is scalar.
Interesting.
But it is instantaneous because the whole solar system is made of scalar. So light only comes into contact with magnetism or heat in some way and shows itself. And based on the amplitude of that, it'll show what color it is.
I agree that you could send a lot of information faster than the speed of light. I do not think you could send a message that way. Like, I can't think of something and Nathan's going to pick it up before I even say it. Like, that I don't think you could do. But I do think that you could transfer a lot of data like that. Just not that sort of information. I don't know if I'm explaining that correctly.
It only has to come out in zeros and ones for us to understand it.
That's true. That is true. I'll give you that. I stand corrected.
3D Havoc asks, have I tried to hang the ground wire from the top of the coil? No, I haven't. That's a good idea. I'll try it.
Yeah.
I
That
came a
ground
little late.
wire.
Did I miss an opening or did you go right into Sean's presentation?
No, we went right into Sean's presentation.
Okay. I was just curious.
A lot of talking to each other in the
So-
chat. Awesome.
So, Sean, what's the difference between your sphere and the Death Star that Ian's making? It's
Well,
Ian
he's
making it, yeah?
he's following my specs. To
Oh,
a
okay.
T. He's using the STL 3D print files. Yeah, we've been going back and forth on it. His looks really nice. I can't wait. It's been a process. He also has the exact same ZVS board, and he ordered all the parts. So he's literally has a duplicate. So I can't wait. The only thing I would say is difference. His is that it's perfectly wound. It's everything symmetrical. All the counts are correct. I mean, he even like unwound a bunch of turns of wire because he wanted to make sure it was perfect. And that's something I don't do. I'm like, it works. It works.
Yeah.
So yeah, he's a helicopter pilot. So he's very precise.
That's why. You got to come pick me up, Ian. Come on.
He says it's 4,650 winds. One by one. It's a labor of love.
Wow.
Yeah.
That's a lot of love.
That's a lot of love.
Yeah.
That's a lot of love, yeah.
Whole lot of love.
And you're looking for love in the right places here, so that's good.
That's a
Like-
dad
like
joke
her
right there.
There you go. Just like my dirty joke, the white horse fell in the mud. Total dad joke, man.
Yeah.
Oh my
Yeah.
God. Ben was talking about white holes and black holes yesterday. Oh, I was dying.
No.
They're just the same. They're the flip side of the same coin. That's all. they
Yeah.
are.
Yeah.
Yeah.
I think so.
Yeah, it was just white and it got dirty at some point.
So
There you go.
Wizard of Woodstock says, have you seen the capacitor charge paradox? I wonder if he's referring to the air capacitor or the little tiny capacitor that powers the whole oscillations for the discharge.
What's the charge paradox? Capacitor paradox.
Paradox, is he meaning the air capacitor?
Is that what he means? Like,
I don't know. I'm asking you guys.
oh, I'm not sure either, honestly.
So here's the thing, Sean. We got requests for a pyramid earlier. Now we got another request for an egg.
Yeah,
Well, my sphere is
an
done,
egg.
but I'm not showing people yet.
Egg and a pyramid.
He's gonna keep you working.
I got pyramid in the back of my head all the time. I'm just trying to test the stuff that I built before I move.
I just real quick for you answer. I just want to say a quick hi to Phil out there. He come in and stop by and say hi to the rest of us. So he's got some cool stuff going on Friday. Sorry.
Awesome, Phil. I look forward to it.
Yeah, it's gonna be awesome.
All right, Sean, go ahead and answer the question. Sorry.
No worries. I'm just going through them here. Good stuff. Good conversations. So where does the ether fit in your assumed model? Ian's asking me that. Oh boy, you guys are the ether experts. Help me out.
Well, it depends where your theory is about where it's in your system. I know where it's in my system. I can move it around even.
I
You
don't
can
know
use it.
ether or.
Ether's like the energy between positive and negative. It's like the vibration without frequency. It gives you the ability to manipulate temperature. Hot or cold.
Boy.
And you're there. Like I said, you just don't know you're quite there. It took me a while, I'll tell you. Nathan had to show me about temperature. I left it out of my theory, which was a dumb move because it was never getting hot. So I always thought, well, that's just it. It's cold. Well, where did the heat go? It's got to go somewhere. So you're moving it around, right? And yours is doing it.
But it means a whole lot to how your system works.
Mm-hmm.
So Sean probably doesn't get any heat in the center of his coil. But by the way, when you see the wires coming out of this thing, just so we all know, round coil, wire coming out top, wire coming out the bottom. So he directly tells it where it's at. And this is the form that he gets out of it. That's his null zone. Then he gets his vortex. It's pretty simple in where you put it.
That null zone's important. You can do a lot with it if you understand what that null zone is.
That big sphere that I'm sphere part 2, I'm going to be drilling some holes in it to see if we can put things inside of it. I've had 2 tries to print a transparent sphere and I failed. So I plan on doing it. It's hard. I'm using polycarbonate.
Oh yeah.
Anybody use polycarbonate filament for the 3D printer?
No, but I know an expert in holes.
If he's Canadian, he has 3.
It's Canadian.
Mike will come over with his drill and man, he'll take care of them holes for you.
The only way I know how to use polycarbonate is with a laser printer by cutting a series of different size discs in order to wind it like that. That's my only thought.
I use the soldering iron. I literally just take the plastic and set my soldering iron through it and it makes a hole.
Yeah,
wow.
Yeah, I've done
That's
that.
good. Yeah, I've never tried that.
In ventilation, you get nice holes.
Yeah,
No
works perfect.
drilling.
Melt them.
Yeah.
If you want like super awesome high quality polycarbonate or plexiglass, thrift stores are selling all the LCD monitors that were popular 20 years ago, and $4 or $5 you can get. I got 24 inchers, and I get a thick piece of 24-inch plexiglass or polycarbonate, and it's great for. I mean, you use plexiglass.
Yep. You know where I got those from? In 7-Eleven, you know all those plastic racks where they put all the candy and stuff? That's what those are.
Oh, interesting.
Yeah, I knew the manager. So he's like, oh, yeah, you can take them. We're redoing the store. Like, thanks.
Nice.
Yeah, leave it out. Leave plexiglass out in the heat if it's the right type and thin enough.
Yeah.
It'll start bending to the shape that you put it on. So
Nice. I didn't think about that either. Wow.
So
when you get an old TV, I think it's the plasmas, might be the LEDs, and it's 42 inches and bigger. You get a Fresnel lens out of it, and you can literally like cook your dinner with it.
It's the white sheets that are in there.
Wow. Yeah, Fresnel lenses are really powerful at magnification.
Yeah, they are.
They use them in lighthouses.
I've seen people cook rocks with those things.
You can melt lead with them.
Yeah.
So if you guys live in the States, go to Facebook Marketplace and look for rear projection TVs. People don't want them. They literally will give them to you for free.
Yep.
And then there is 2 massive Fresnel lenses. Minimum. You get 3 really nice flybacks, the big ones. You get all kinds of goodies on that rear projection, and everybody wants them out.
Yeah, they're like a candy store for electronics.
Yeah, and you can't throw them away. They won't let you throw them away.
Yeah, we have people, by the way, that collect TVs and stuff like that for electronics in California. So they'll show up at a burger place and collect them all. So you just get the guy's number, and he'll pull all the coils for you. And you could just buy the whole lot of them from them.
Oh, wow.
Because they're going to junk the TVs and try to properly take care of the rest of it. So they sell the circuit boards really cheap.
Huh.
So,
that's awesome.
Yeah.
That's a good resource.
Yeah. Well, for as many as I blow up, you got to have one resource like that.
I have a 14-inch TV sitting beside this one I use for my old Pac-Man and Miss Pac-Man and stuff. So still works. It's like 50 years old. What's that?
Is this your man cave?
Part of it.
Nice.
Yeah. It extends. It's pretty big.
Are you in the basement?
Yeah.
Nice.
I can only do certain experiments in my basement. I have a garage that I do the crazy stuff in. Just because, right?
Yeah, garages are really necessary for that crazy stuff. I was just going over that with Sean earlier. I was like, I really need a garage to do some of the stuff that I really want to do.
Yeah.
Well, nobody lives above a garage, so you don't have to worry.
All that extra smoke in your garage, you got to blow it out through the big door.
Blow it out your holes.
I got a chimney. There you go.
So Wizard of Woodstock says Don Smith used a cap on his ground line. It increases the displacement current.
Yep. Yeah,
I'm
glad you brought that up. That's actually, I use a high frequency capacitor for that.
So what does that mean?
Can you explain that just a little bit?
Yeah.
Okay, so from the coil to the ground, rather than going just to the pipe underneath my house, stupid knob, I go from the coil as a ground to one end of the high frequency capacitor, then from the high frequency capacitor to the ground under my house. So it has to go through the cap before it gets into the earth. And you would think you're not getting anything out of that. The minute I did that, I was getting 1.5 volts without even pulsing the coil.
Wow.
Yeah. Just by hooking it all up. As soon as the circuit was complete, the meter collected 1.5 volts. So there's something there. That mechanism is in play, and you get just that little bit extra with that capacitor there.
Interesting. Very cool.
Somebody asked, Pac-Man, Gerald, is that why you weren't ready last weekend?
You say a hack?
It was Pac-Man. He asked me if it was Pac-Man. No, it was Miss Pac-Man, okay? I mean, hey. Kidding.
Gerald was playing with all the ghosts.
That's it. Yeah. Sending them back from which they came. Kidding. I got that Ghost Busters patch, like one of those originals. So I sewed it to my vest. The vest where I keep all my things that could be needed in case of a bad situation. So here I am. You're gonna look at me and be all, that guy's serious. Then you're gonna see this Ghostbusters patch.
Oh my goodness.
Got a question, right?
Wow.
Anyway, just thought I'd bring that up. Should we address? Are you? Did you get any more questions, Sean?
Yeah, I'm just going through them. I got the question again about familiar with the capacitor charge paradox and its solution. Oh boy.
What is the capacitor charge paradox?
Here's a good one. Wonder if a humidifier would change the capacitance in the room. Oh, I believe that totally.
Absolutely, it does.
Absolutely. I'm wondering if more water in the air would lower the capacitance versus dry air, higher capacitance. Like that would just be really cool to
yeah, so don't fart.
You don't want to change the capacitance.
All that hot air.
Yeah, you don't want to direct short.
Can you imagine that, dude? Your pants light on fire because you're over there playing with your testicle and you're blasting them out. Like you get this big voltage of lightning coming out your rear, and then you're just everything's on fire.
Oh, that's funny.
Can you imagine doing that to your kids as you run in the house?
Hey, we used to do it in high school with jeans. You just lift up your leg with a lighter, and it would just be like,
yeah.
Oh my goodness.
Oh, that's
Crazy.
so bad.
Man, crazy stuff.
Dude, if I knew it worked, I would try it just to get the video of it. Even though it would probably burn and singe everything in the backside.
You gotta wear jeans, man. It's the only thing it doesn't go through, and it does this like weird cloud flame. It's really cool.
It's all green.
Yeah.
Oh my goodness.
All right, we're gonna have to work on that capacitance thing there, Sean.
Yeah, I looked it up there. It's the two capacitor paradox. It's a thought experiment in electric circuit theory.
Okay.
Oh, it's a big explanation here.
I'll have to look it up.
Yeah.
Thank you. Let's see, other questions. Let's see, sound travels faster than light. That's interesting. Let's see. There's a cat near a router.
Yeah, I'll have to deal with it.
Oh boy.
It's the cutest interruption in history, ladies and gentlemen.
Yeah.
Hey Ben, what'd you think of the presentation? Do you have any questions?
No, I didn't have any questions immediately, but to be honest, I had a phone call and I missed the first part of it.
Oh,
and
no.
I really wanted to see what you had to say about your interpretation of how electrons flow, and that's right when I got the phone call. So I have to go back and watch that. But in terms of what you were showing, all your videos of your arcs and stuff, that was really neat. I like how you actually did a diagram and showed where the wire was going to the ground. And it kind of gave me a visual of the circuit that you're creating in the air.
Oh, yeah. Awesome. Good. Glad to hear. That's my hope, is to just clarify things. Or, I mean, I didn't know electrons move that slow. I mean, it's just fascinating. I knew the charge moved fast, but yeah, they move slow. I think there's someone the other day said that there's no such thing as electrons.
Yeah, that's an interesting theory too. Like they're just a concept made up on paper to explain some other phenomenon.
Yeah.
ultimately, we don't really know. We have ideas. They're all theories in the end, right? But if we
Right.
can make the electricity flow or the lights turn on, doesn't really matter how you describe it, in my opinion. As long as when
So-
you hit that switch, it goes.
Right.
Yeah.
So Sean, you just summarize real quick if you can. Like, you said that you think electrons flow really slow. Can you like just elaborate on that real quick? Because I missed that part.
Sure, sure. So if you could imagine a long pipe with around the diameter of a ping pong balls, and then you can fill that pipe up with ping pong balls. If you were to add a ping pong ball on one side, sort of hammer it with a rubber mallet, and then another ping pong ball would fall out the other side, you would cause quite a bit of agitation or excitement to the ping pong balls in the middle of the pipe. Even though the balls are moving slow, that excitation creates both a magnetic field and an electric charge field. And the magnetic field and the electric charge field, they travel near the speed of light. They travel outside the wire.
Oh,
And
I see what you're
so-
saying.
And the electrons move 1 inch, 30 inches an hour. So if you have, like, let's say an appliance and it has a 30-foot cord, 30-inch cord, it would take a whole hour for the electrons to go from your wall socket into your device.
Wow. So if you wanted to prime your system with electrons, it would take a while. You're saying that's the electricity is created by the disturbances between those electrons.
Exactly. Yeah. It's the
Wow.
excitation of the electrons. And what's interesting about the plasma, I didn't mention this in the presentation, but when we trick the electrons to go to the tip of the wire, and that's the whole idea about not having any sharp edges, because electrons will be tricked to go out on it because they repel each other. They think, oh, I've gotten away from my friends. And then all of a sudden, more electrons come on that same point. And because they repel themselves, they're pushed off the point. And so here you have these electrons flying through the air, and they run into atoms. And when they run into an atom, it excites the atom to another energy level. And so, for instance, an electron hits, let's say, an oxygen atom. That's actually, it's an atom. Molecule, sorry. And what it does is it causes an excitation that moves the electron up to a different orbit. Now, once the atom, the molecule then stabilizes, and I can't talk. The electron falls down to the stable orbit again, it emits a photon. And that's what we're seeing are the photons of light. We're not seeing the electrons or protons. We're seeing photons. And those photons are created from the electrons returning to their normal state when they're excited by the plasma.
Yeah, when they restabilize.
Right.
That's cool. Hey, Sean, we have a conspiracy growing over your high voltage probe.
Oh,
Did Gerald draw the circuits for that?
high voltage probe?
No, that's all him, Matt. Like that, he did that, right? That I didn't draw that. I'm not allowed. I've been denied the pen.
Oh my! I'm dense. Okay, I get it now.
There was only one, Sean, that I went. I could have been the one to draw that. We're gonna laugh.
Oh my god!
So yeah, it was good. There's just one.
Yeah, I can see that now. Bad. Oh my goodness.
Yeah. It's awesome. It's awesome.
Well, oh man, the visual on that was amazing.
Yeah,
horrendous. I got to take it out now because this is PG.
Well,
this is
it's
not
a nice red
That's
color.
too big.
Oh my goodness.
Squiggly lines and stuff. Sorry.
Oh, sorry, Sean. I apologize.
No, too funny. Too funny.
Talking about the Kama Sutra here.
There you go. I studied that. It's a good book. Anyway.
Oh,
Grab a flyer questions here. I went and for the first time watched the footage of the grab a flyer operating by the inventor guy when he was wearing the silver helmet. And I want to go on the record and say, I know it was. Okay. Sorry. I thought that was a question.
no, it was what?
That's the end.
What?
It's the end of the comment.
Oh, I thought you were trying to make a statement. I'm like, I'm waiting for the rest.
Sorry about that.
It's okay. Yeah, so I meant comma as in CAMMA. Like a pun.
Oh,
I'm not touching it. I'm leaving it alone. There's so much. I go so many angles with that one. You're just lining them up, Ben. It's like crap.
I'm sorry, Gerald. I'm sorry. I didn't mean
All
to.
good, brother. That's all. I just kind of get us in trouble.
always in trouble.
I really enjoyed the enthusiasm, Ben, when the neon bulb flickered.
Oh.
Oh,
that
yeah.
scream!
Ben squealed like a girl.
I just
Yeah.
fell out of my chair.
I'll tell you right now, if you ever want to hear me scream like a little schoolgirl, go on the live stream from the other night.
I haven't seen it. I'm going to watch it. I'm going to clip it, and I'm going to make it part of my alarm system.
Dude,
Gerald.
it will wake you up.
Walk into my backyard, all you hear is Ben scream.
Oh my God. Hold on.
Your video with the ball lightning, if you wouldn't have put that out, if you didn't discover that in your system and explain it, I would have never discovered it in mine. And I did. I saw the same friggin' thing.
Didn't you? I missed
Yeah.
that. Good for you, Ben.
It wasn't as
Good for you.
intense, but you saw it. It was so cool. Yeah. And I wouldn't have known if you didn't put that video out. I would have no idea. I would not have known to look for that.
It gets more intense. It doesn't go just purple. It goes purple, pink, blue, and it spins. It looks just like
Oh,
out
wow.
of this world.
Yeah, so you got like a lot more of it in there, and that would be cool to see it like off camera. You know what I mean? Because the camera kind of obfuscates it with the light exposure.
It does.
but-
It messes with the camera a little bit.
Yeah, I wasn't positive if they would even pick it up on mine because it was so slight. You know, because at first it was like just a pink, and you could see the purplish doll. And I'm like, that's not gonna pick it up, but it did. I was like, wow.
That's cool.
Oh.
All right, guys, they got something to share for you.
Sure.
Uh-oh.
Yeah.
Go, Ben, go.
Ben was dancing the whole time you had this. I had to make him a short for it.
Go, Ben, go. Woohoo! Just forgot the bowl.
Oh, look at him look over his shoulder. Look at that.
That's funny.
Reminds me of the American Pie movie.
Oh my goodness.
The only thing it's missing is the scream at the end. Like as if he's getting into it, then
We need the scream. The scream
You know?
is
That's
great.
hilarious. That's
Kinda
great.
like
Yeah, I
that.
love that. Thank you.
Oh, Ben, I had to put that up, man. That's
that
absolutely
rocks, man.
amazing.
Good for you, man.
I didn't think about making that a short, honestly, so I appreciate that.
That's
Dance
awesome.
that shit away, man. I'm telling you. You're
Oh,
not married, you will be soon.
yeah.
Dancing is like anyway.
See, the music was perfect for it, though, too.
Yeah,
Yeah, perfect.
that's great.
Oh, man. Sorry.
Try to
know you
make
guys
it
are
fun.
talking other stuff, but I had to show it.
Yeah, no, it's I appreciate that, Nathan. I try to make my videos fun, you know.
You do a good job, man.
It made my day.
Thank
I
you.
can tell you that right now.
Yeah.
Hey,
Have
gents,
fun
I'll be
with
right
it.
back.
Sounds good.
Thanks.
Okay.
So I have
Go
to
ahead.
take off in the next 15 or so.
Okay,
Unfortunately.
well, if you don't mind, I had something to bring up, guys.
Dress
we
the
had-
elephant in the room.
Huh?
Dress the elephant in the room.
Yeah, I'm gonna have to. So guys, we all kind of got hacked. So Gerald got hacked. You saw it during his presentation. I got hacked 2 times the same week. I don't know if Ben did. I know Victor got hacked. So we all opened the same files. So it's the same person sending them out. So just so we all are clear here, there's a bad apple in the bunch, and we all talk to each other, and we will no longer be opening those on the show or bringing some of those folks around. So it was just a weird thing. It happened, and we're best to just walk away from it. So I have to address it. You know what I mean? Because people have been asking in the chats and stuff like that of what's going on. So, yeah, it was definitely somebody hacked all of our systems. So somebody's out there, and I don't know if it's the government or just another group or what it is, but we're trying to put out the tech for free. So why they would even do that is beyond me, but they did. And we figured out who it was based on you know, who did what and who opened what, and we figured it all out. So it's a big S show, and you know, we
Sorry,
just
I had
kind
to
of
play a little bit there. I had an idea, and the hat didn't work for the thing I was trying to pull off there. But you're not wrong. We know exactly who it is. I suspect why. I'm sure you guys have the same suspicions. The minute that we decided to put my theory out, and Nathan was so gracious to promote me, amazing job. And to all the subscribers out there, thank you so much.
Yes.
Awesome. I can't thank you enough.
Very cool.
But unfortunately, bad apples do get in the way. And that's kind of where we're at. I'm going to release my theory. Nobody's going to stop that, not unless they put a bullet in me. Let's hope that doesn't happen. But basically, I'm going to do it on my time and my way. I'm not going to promote it. I'm not telling anybody. You're just going to either have it one day or you won't. It's all been written down. It's been forwarded. I've put it in registered mail and sent it to myself and to 4 others. I'll never open it. Therefore, it's now a legal document. So the theory's out there, and it connects not one theory, not 2 theories, but it takes a piece out of maybe 3 or 4 different theories that are massive out there. And the math is in there, not my math. But like I said before, when I brought this system out and started talking to the scientific community, it wasn't to find something that I was looking for. It was to explain what I have. Unfortunately, there's people out there that don't like my beliefs. That's fine. My beliefs do not require you to. But if they're getting in the way, if you not liking my beliefs is getting in the way of others actually benefiting from this tech, you may have to answer to that one day. It won't be by my hand or by me, but we know who you are, and just going to leave it at that. Good luck.
Yeah. So let me address another thing here, guys. With what just happened, we had a thing added to our streams, and we all got strikes for it. So we no longer will be adding things to our streams unless we're in it. So, yeah. I mean, if Bernie was here, he'd be in the stream with us, but he's not here, so he wasn't put in the stream. So I hope you guys understand that we were not suggesting in him on that last one. It's just this one here. It was
I wasn't even intending on streaming this on my channel just because I was expecting to come in and out of the stream. I wasn't expecting to be here the whole time. But you know, this is more of like your guys' thing anyways. So this is your show. It was always weird for me to stream it on my channel. It helps boost my numbers, but at the end of the day, I'm good. If I'm not here, I don't need to stream it on my channel. You know what I mean?
I don't think that was Nathan's point, though. I think if you're in it, it's okay if you stream, but you have to be in it.
That's exactly what I'm saying.
Am I wrong?
Yeah,
No, that's right.
No, that's right. So I just want to put that out there. Okay, nothing against anyone else. It's just we don't like strikes on our channel, and we knew to avoid the whole issue of it, and it happened anyway, and none of us was there in the feed to stop it. So we just, I make it basically, you want to blame somebody, blame me. I'm making the decision to say I'm not putting up with that, so we're just going to be done with it. So
Yeah.
It's just a lot of variables.
Yeah, it's you could just put the whole thing on me, guys. It's not a problem.
I'll take some. Oh, sorry.
I control the StreamYard, so I allow things to happen, and unfortunately, it bit us in the backside, and hopefully, it'll be cleared up and done here shortly, and we can all go back to having fun and doing crazy things, because that's all we really want to do. I mean, look, just understand who we're reaching out to here. We reach out to everybody who's kind of like been shunned by everybody. Everybody kind of kicked to the curb, who said wasn't good enough, said
or didn't have a PhD or an MP3,
Yeah.
There you go. So, you know what I mean? And the people that come in, they're kind of not as, sometimes, I don't want to say this in the best way possible, they're keeping to themselves because they don't want to be ridiculed by everyone else. And
that's a good point.
we leave
over.
Yeah, we have a safe environment here, and that's what we're trying to continue. So when we make these changes, that's all it is. So just
a good way to put it.
Yeah, because
and this StreamYard's account, Nathan's generous enough to let us use. This is your account, and it's expensive. It really is. I'm not gonna lie, I wouldn't be able to afford it.
I don't know if you guys feel this way, but I certainly do. It's difficult for an inventor to come out and display what he's invented, let alone put himself out there, display who he is, display what he's done for people to critique. And then you get some Dingledorf messing around with his computer or messing around with his reputation just because he wants to be the one to have his name on that paper. He wants to be the one to go, I'm famous. You want the fame? You can fucking take it. I don't give a shit. I want this stuff to get out to the people, because the people need it. I don't care about fame. The people that do, I'm sorry, but it's a little pathetic. Just saying.
Yeah,
there's a greater purpose to all this. It goes beyond us. It's beyond us, really.
That's the way. Yeah, I think so. And if I'm wrong, I'm sorry if I kind of put you guys on the spot.
I think I agree. I generally agree with you, Gerald.
Fame is lame.
Yeah, fame is lame.
Anyway, guys, I didn't want to bring the mood down. I had to address it. It's something that has to come out. So I don't want any, anybody lingering out there. This is just what we did. Okay, we made a few decisions to change some things, and hopefully it'll get better for all of us, because I want to continue to bring more people in, more people to show what they do, present what they have. Look, we're not against physicists. We just would like you to come on and present, and we'll all read your papers and help you out with the mechanics of things. So if you have a question at that time of how something's built, this is like the best forum for you. You know what I mean?
Mm-hmm.
This is the fringe. The fringe is outside of academia, outside of the normal.
Yeah.
We're not looking to, keep people happy in the scientific community. We're here to help those that have that hard time putting themselves out there. And you can always do this and still give your presentation and have no issues whatsoever. Heck, I was behind my screen for years. People didn't even see my face, right? So that's what this group is for. We want the ones that are so far out, you barely see them, and we got to pull them in. The fringe.
I owe all of my revelations to this team. I wouldn't be here in the state of my research that it's at right now without this team. So absolutely not. I would be on a completely different path, probably lost in the woods somewhere.
Metaphorically.
I lived in the woods. It's fun, but
yeah, metaphorically, exactly. Yeah.
We're gonna move to Sean's woods.
Yeah.
Yeah.
That's where we're going.
It's south for you, Gerald.
That's okay. I'll be there.
We're getting a little canoe.
I'll come build you a bunker.
A little tiny.
I've got a backhoe.
There you go. I worked on foundation work for 10 years. Built underground parkades. I know about concrete.
Oh man, can you imagine that? We're all in a teepee over there on Sean's property. We're all getting in the smoke and then going in mystical trips as far out as we already are. We're gonna go even further.
You kidding? With Sean's help, we put the team together where his prop would be open portals to different planets by that point.
Yeah.
Smoking the peace pipe.
There you go.
Hey Sean, there was a lake here, but we transported it to Mars for you.
Thanks a lot, guys.
That's awesome.
We only found the Loch Ness monster at the bottom of your pond, nothing else.
Oh boy.
As long as he's dead. It's big.
Yeah, we're okay.
Yeah.
He's talking, but he's not moving his lips.
Oh my god.
Oh my god.
Oh, I could go
So funny.
places with that. I'm leaving it alone.
Boy.
Oh man, we have too much fun. All right, guys. Sean, thank you for presenting today. I really do appreciate it.
Thanks for having
thanks,
me.
Thanks, Sean.
You guys are great.
And according to Ben, just don't forget to.
Oh, we're showing that on the way out, guys. We're replaying that. I love that, Ben.
Seeing you guys in the chat.
Yeah, thank you guys. Been awesome hanging out with you guys today. Gerald, we're happy you're back, buddy. So
yeah, I'm glad to hear
there
from
was
you,
a
Gerald.
question they wanted to know how soon. Sooner than you think, but I ain't gonna say when.
there you go.
Oh, real quick before we end, we didn't have time to go into it, so I might do a separate live stream just because we're going over here. Where I'm gonna run a couple of tests with the coil. So I just want to let everybody know that.
Did you have a quick video you want to show us, Ben? Like when you screamed?
I mean, I could show you a quick video of last night, but I don't have anything prepared. No, the only thing I have really is 2 pictures of the finished version of the advanced version 3 coil, but I'll save them for next time.
Okay. Sorry about that, Ben.
No, it's good. This test I'm gonna do is not gonna be a short test, so it's gonna take maybe an hour to do. So it wasn't something that I expected to get to. Just if we had time, kind of thing. If nobody had anything to present at the end of the show.
Okay.
Well, it sounds cool.
Ian's cracking the whip. He wants to see some of my circuits.
Everybody wants to see him, Gerald.
They're very simple. On Friday on Mike's station, is he still doing his thing this Friday? Yeah.
This is the last one before he takes some time off.
Or did you want me to wait till next Wednesday?
No. Here's what I'd like you to do, Gerald. Draw him the schematic, send them to me to my email. And I will properly draw the schematic without the extra parts.
Nathan, what are you saying? I don't know. You're saying I don't know how to draw? I can't even
Not at all. We end up with a lot of extra parts in there.
Yeah, that's fine. We'll do that. I like that idea.
Yeah, let's just do that.
Yeah.
And I'll just send them via email to Ian, but I'll release them on my channel as well. That way he has them. But
that's fair. That's cool. I have no issues with that. Whatever. I'll do the schematic, and if you want, do the video on it. The last time you did it, you did an awesome job. I couldn't have done better. So
right on.
Yeah, I'd be honored. That'd be awesome.
Cool. We'll do it that way then. That way it's a done deal. All right, guys, we all ready to have a little fun on the way out.
All right.
All right, Ben.
Thanks,
Thank
Ben.
you for this video.
Thanks, guys.
Thank you in the chat. Everybody, go ahead.
Oh yeah. Free energy funk now.
How does he do that?
I love that.
All right.
Oh, he's doing the butt backwards, right? There you go.
Oh man, you guys are awesome.
Oh god.